Hello everyone, in this video we will be discussing Chapter 15, Odds and Risk Ratios. As always, I start with a chapter overview slide. We will be discussing the purpose of these two ratios, the hypotheses of the odds ratio test, how to calculate the odds ratio, the confidence interval for the odds ratio and the risk ratio, the interpretation of these ratios, and worked examples. Odds and risk ratios are used for 2x2 tables. This is important because we often see 2x2 tables in medical and clinical studies. The odds ratio is used to measure the association between a property X and a second property Y in a population. The odds ratio tells you how the presence or absence of property X has an effect on the presence or absence of property Y. Importantly, the odds ratio value alone does not indicate statistical significance. For this, we need to calculate the confidence interval and p-value. The risk ratio measures the frequency of property Y in some population. It tells you how much more or less likely Y is to be in each group in that population. The hypotheses of the odds ratio test involve the relationship between the first property X and the second property Y. The null hypothesis states that there is no relationship between these two properties. This would be reflected when the odds ratio is close to or equal to 1. The alternative hypothesis is that there is a relationship between property X and property Y. This is reflected when the odds ratio is not equal to 1. To calculate the odds ratio, we look at our 2x2 table and we assign each value to the variables A, B, C, and D. The order of these variables does matter, and as you can see here, A and B are in the first row of this table, while C and D are in the second row of the table. The table is organized so that the properties X and Y are in the first cells, and not X and not Y, their complements are in the second column and row. If Y is present, the odds of having property X are A to C or A over C. If Y is not present, the odds of having X are B to D or B over D. To calculate the odds ratio, we use the formula A over C divided by B over D. Now let's look at two examples from the lab manual on how to calculate the odds ratio. In this example, there are two categories. The first is behavior type, risky or normal, and the second is health, sick or well. Remember, for the odds ratio and risk ratio calculations, we use the variables A, B, C, and D. In the first table, if you are sick, the odds of having risky behavior are 20 to 10. If you are not sick, the odds of risky behavior are 80 to 90. To calculate the odds ratio, we do 20 over 10 divided by 80 over 90, which gives us a value of 2.25. In the second table, we have the same categories and the same values for sick, but we now have greater values for well. This means this is a greater sampling of the population. In this example, calculating the odds ratio would give us 20 over 10 over 980 over 990. This gives an odds ratio value of 2.0. To calculate the confidence intervals for the odds ratio, we need to use a different type of distribution. This is because the distribution of sample odds ratio values is not normal. Fortunately, the natural log of sample odds ratio values does follow a normal distribution. To calculate the confidence interval for the odds ratio, we first calculate the standard error of the odds ratio. This is equal to the square root of 1 over A plus 1 over B plus 1 over C plus 1 over D. Next, we calculate the 95% confidence interval for the natural log of the sample odds ratio. This is using the equation natural log of the odds ratio plus or minus 1.96 times the standard error of the odds ratio. Finally, we calculate the 95% confidence interval for the sample odds ratio by raising each of the upper and lower bounds of the natural log confidence interval by exponent e. To calculate the risk ratio, we use the same type of table and variables. Remember, the risk ratio measures the frequency of property Y. The proportion of risky people who are sick is equal to A over A plus B. The proportion of normal people who are sick is equal to C over C plus D. To calculate the risk ratio, we use A over A plus B divided by C over C plus D. To interpret the odds ratio, we compare it to 1. If the odds ratio is equal to 1, this means that property X does not affect property Y. If the odds ratio is greater than 1, this means that property Y has higher odds of occurring when property X is present. If the odds ratio is less than 1, this means that property Y has lower odds of occurring when property X is present. For the risk ratio, we do something similar. We compare the risk ratio to 1. If it is approximately equal to 1, this means that there's the same likelihood of that property occurring in either group. If the risk ratio is greater than 1, this means there is a greater likelihood of that property occurring. There are two ways this is often written in literature that are listed here. First, patients who take aspirin are 1.084 times as likely as other patients to have some property. Another way of saying this is patients who take aspirin have an 8.4% higher chance of some property than patients who do not take aspirin. On the other hand, if the risk ratio is less than 1, this means there is a less likelihood of that property occurring. For example, patients who had an appendectomy had 0.58 times the risk of some property than patients who didn't, or patients who had an appendectomy were 58% less likely to have some property than patients who didn't. Now we will go through a worked example in Excel and two worked examples in R. First, I'll open up the lab manual to take a look at these examples. These are the same numbers we saw in the PowerPoint and the same categories. We have the behavior category and the wellness category. So we'll be using this example in Excel and in R, and we'll be using this example with a greater number of people in R. In the Excel template, we have worked example 1 and there's original data. The hypotheses for the odds ratio test talk about the relationship between the two properties. The null hypothesis here is that there is no relationship between health and behavior. And what this would look like in terms of the numbers is the odds ratio is equal to or close to equal to 1. The alternative hypothesis is that there is a relationship between health and behavior. And this would look like the odds ratio does not equal 1. First, let's calculate the risk ratio. This is using the formula A over A plus B over C plus D. So we need to be very careful with our parentheses use here. First, we have A over A plus B. Here is A divided by, we need another set of parentheses for the denominator. We have A plus B. And we need to close the first set of parentheses because this is the entire numerator of that equation. This is all divided by C divided by C plus D. And again, we need parentheses around this denominator, and we'll finish out our parentheses like this. We get a risk ratio of 2.0. Now let's calculate the odds ratio using the formula A over C all over B over D. Again, being careful with parentheses, we have A divided by C all divided by B divided by D. Here we get an odds ratio of 2.02. In order to statistically test this, we need to calculate the confidence interval, and one of the variables we need for the confidence interval is the standard error of the odds ratio. This is with the formula the square root of 1 divided by A plus 1 divided by B plus 1 divided by C plus 1 divided by D. Here we get a standard error of the odds ratio of 0.39. Next, to calculate the confidence interval of this odds ratio, we start with the natural log. Remember, because the sample value does not have a normal distribution, but the natural log does. The formula for the lower bound of the natural log confidence interval is natural log of the odds ratio minus 1.96 times the standard error of the odds ratio. This gives us a lower bound of negative 0.061. For the upper bound, we have a similar formula, natural log of the odds ratio, but this time adding 1.96 times the standard error of the odds ratio. And here we get 1.468. To convert these values to the regular confidence interval instead of the natural log confidence interval, all we need to do is use exponent on that value to get 0.941 for the lower bound, and same thing for the upper exponent of the natural log upper bound to get the regular upper bound. So all in all, our confidence interval with the actual odds ratio is 0.941 to 4.338. Now comparing this value to 1, since the confidence interval contains 1, this means that the odds ratio is not different enough from 1 to be considered not equal to 1. In this case, the odds ratio is close enough to 1 to be considered equal to 1, even though it seems quite different. The 95% confidence interval tells us that in this case, the odds ratio is equal to 1. What we're going to do next is do this same problem in R, so we can look at all of the statistics together to make our conclusion. In R, I'm going to open a new script, and there are two things we have to do here that will be new for using R. The odds ratio function uses a different library of tools than we've used before in base R. So what we need to do first is we need to install those libraries. And before I do that, I am going to make the text a little bit bigger here. So the first function we need to use is called install packages. And the library that we need to install is called EpiTools. You only have to do this step once. It might take a little bit of time. As you can see here, this is already installed in my version of R. So you only need to run this line once. The next line you do need to run every time you open R and want to run the odds ratio test. This function is called library, and you type in the name of the library, EpiTools, and running this line will load in all of the functions associated with that library. So again, you only need to run line 1 once, then run line 2 to load those functions. Now we will load in the data from this problem using the same method we did in the previous video. Here we will use the function matrix instead of typing the data into a CSV and loading it in. For this, I will call the variable risk, and I'll use the function matrix to assign this data. We need to then have a C for columns, and remember that R likes the data in column format rather than in row format. So taking a look at the original data, this means we need to start with the first column, sick, and then do the numbers in the second column. So this would be 20, 10, 980, 990. So let's go ahead and type that in here. 20, 10, 980, 990. And the second argument for the matrix function is to tell it how many rows should be in this matrix. For this, we'll use the argument n row equals, and we want 2 rows. When we run this line, we see that it successfully assigned this matrix to the variable risk. And we can take a look at this variable by highlighting the word risk and just running that. And we see we have 20, 10, 980, 990, but we don't have any information about the column or row names. So let's go ahead and assign those here. We'll do that in the same way we did in the previous video, using row names of risk, arrow C for column, and the order of our row names was risky and normal. We run this. Let's go ahead and look at object risk again. And now we have our risky and normal row names. Next, let's rename the columns using call names of risk, arrow C. We had sick and well. Let's go ahead and look at object risk one more time. And it looks like I put an extra parentheses there, so I'm going to go ahead and delete that. Rerun line 7 and 8, and now we have risky, normal, sick, and well with all of our data. The first thing we're going to do here is just do a chi-square test. And a chi-square test with a 2x2 data will, by default, do a Yates correction. To do a chi-square test, we use the function chi-square.test, and we only need one argument, and that is the data object. Here we see we ran a Pearson's chi-square test with Yates continuity correction. We have our chi-squared value and our p-value. And what I'm going to do is I'm going to copy this value and put it in the Excel sheet so we can have all our data in one spot. And our p-value for our Yates test, put that here. And already we see that this p-value is greater than our alpha of 0.05, which would tell us to accept the null hypothesis. But before we do that, we're going to also run the Fisher's exact test in R. And to do that, we use the function fisher.test with the argument risk, the object. And here we have the p-value from the Fisher's exact test. And that I will also copy into Excel. Before we talk about our conclusions, I do want to show you the odds ratio function in R. This is a much easier way to find that 95% confidence interval for the odds ratio rather than calculating it in Excel. To do this, we'll use the function odds ratio, and this function is coming from this package called EpiTools that we had to install and load. This will take 2 arguments. The first is the data, risk, and the second, we need to set the method to something called walled, and it will always be walled for this odds ratio test. When we run this line, there's a lot of data. I'm going to open this up a little bit more so we can see it. So we ran the data on risky, normal, sick, well with our numbers here. It did some calculations in here, but what we want to look at is the odds ratio with the 95% confidence interval. The way to read this table is the value here in the second row is the odds ratio. Here it is 2.0204, and we can check that in the one we made in Excel, 2.02, and those match. Then next to that is the lower and upper bound of the 95% confidence interval for the odds ratio. So we have 0.94 and 4.3. Taking a look in Excel, those do match the values we calculated earlier. So with just one line in R, we did the same test we did that took multiple steps in Excel. Now let's take a look at Excel and come to some conclusions about this data. First, our statistical conclusion, whether we accept or reject our null hypothesis. Based on the p-values from the Yates and Fisher's test, these tell us to accept the null hypothesis. But more importantly, from the 95% confidence interval, which includes 1, this indicates that we need to accept the null hypothesis. So I'll type that out here. Accept null hypothesis. P is greater than 0.05, and the 95% confidence interval contains 1. Biologically, this means that there is no relationship between the two properties. And remember, the two properties were behavior and wellness. So there's no relationship between behavior and wellness. Another way to say this is risky behavior does not affect health status or wellness. With that, let's go back into R and do one more example, this time just using R. In this example, I will use the variable more risk because we have more people in this population that we sample. And I'll load it in the same way, matrix C, and this is using the same set of categories, but we have different numbers. So now we have 40, 20, 1960, and 1980. We still want 2 rows. Loading that in, and let's take a look at that either by typing in the variable name or highlighting and running just the highlighted portion. And we again have these unnamed rows and columns. So what I'm going to do is I'm going to actually copy the 2 commands here because the row and column names are the same. And I'm just going to copy and paste the variable name more risk into where risk was. When I run those lines and look at more risk again, I see that I now have the correct row name and column names. Last thing I'll do here is run the odds ratio test using the more risk object and the method equals wald. And running this and looking straight to the odds ratio with 95%, we see we have the same odds ratio, 2.02, but a different lower and upper bound of the 95% confidence interval. In this example, the confidence interval does not contain 1. This means that the 2 properties are related in some way and they affect each other. For this one, the conclusion of this test, even though it has the same odds ratio as the first test, will be different. And I'll write that conclusion here. I'll say since the 95% confidence interval does not include 1, we reject the null hypothesis. Again, that null hypothesis being that the 2 properties are not related. This means that risky behavior, or just behavior, and health or wellness are related. Finally, since the odds ratio is greater than 1, that is, this 2.02 value is greater than 1, we can conclude that risky behavior appears to increase the probability of being or getting sick. Let's go ahead and save this script. And I will, as always, save it to my desktop. And I'll call this Chapter 15, Odds Ratio. And that concludes our video on Chapter 15.